Hi, my name is Dylan Stinson, and in this video I'm going to demonstrate the basic procedure for designing and verifying the performance of an antenna matching circuit to be placed between an antenna and a wireless transceiver module. I'll be using the TTR500 Vector Network Analyzer in combination with Optenilab simulation software. With the rapid increase in IoT and wireless-enabled products, more and more customers are having to integrate an off-the-shelf antenna or design their own custom or reference antenna to go with an off-the-shelf wireless module. But what they're finding is that the impedance of the antenna rarely ever matches the impedance of the wireless module. And this is important because the impedance mismatches can cause reflections in the feed point of the antenna. Now, these reflections can cause the signal to not radiate fully out of the antenna, which can ultimately result in reduced data packets, reduced signal range, and wasted battery life. That's why it's important to characterize your antenna system with a VNA and ultimately use a matching network to improve the matching between the antenna and the wireless transceiver module. Here you can see I have a simple whip antenna, and for the purpose of this scenario, the goal is to get the antenna to match the impedance of a 50 ohm transmission line. And to do so, I've created a simple matching network test board. And the test board will allow me to properly calibrate the VNA, measure its input impedance, including the feed line, and then design a matching network and measure the performance of the matching network. And for this measurement, I'll be using the TTR500 Vector Network Analyzer. Taking the impedance measurement data that I'm going to get from the VNA, we'll be able to design a two-component lumped matching network using circuit simulator software. And one thing to keep in mind when matching, you want to minimize both reflections and circuit losses. So that's why I'll be using low-loss inductive and capacitive components for this matching network. The first step is to calibrate the VNA as close to the location of the matching network as possible. In this case, it's the end of the type N to SMA connector. And then to get the calibration plane to the location of the matching network, we're going to have to apply a port extension. So first, I'll calibrate using my my 3.5mm spinner cal kit at the end of the type N to SMA connector. Now that we've properly calibrated at the end of the type N to SMA connector, now we need to apply a port extension. And to do so, I've conveniently included an equivalent trace on my test board with an open located exactly where the matching network is to be placed. And I'll use this open on the Smith chart to indicate when I've applied the correct amount of port extension. One thing to note, on a real-world transceiver module, you can create an actual open by just removing the components that are already in place for the matching network. That's if it's already included. Here I'm measuring S11 on the open trace using the Smith chart of VectorView PC. Now if you remember your Smith chart basics, the point farthest to the right represents an open. And so, therefore, I'll know when I've applied the correct amount of port extension when I read an open on the Smith chart. Let's go ahead and add a port extension and see if I can get our marker to lie on the open mark. So I'll go to Cal, port extension, enable. Let's try 3.5 centimeters. And click apply. See where this puts us. Almost there. Let's try a little bit more. All right, and there we go. So now we've properly moved our calibration plane, so now it's aligned with where we're going to place the matching network. So now that we're measuring the impedance of the antenna, including the feed line, let's go ahead and save the S parameter file so that we can export it to our simulation software. So to save the S parameter file, I'll go to Save SNP, save the S1P on port 1, and then I'll overwrite a file that I created recently. And this will be the unmatched case. Now there are many circuit simulators out there on the market, and Optenilab is really one of the best. So the first thing, since we've measured the impedance of the feed line and antenna, we need to load it into our simulator software. So first I'll go File, read the impedance file, and I'll load the antenna. So you can see here we have our Smith chart on the right, And to generate a matching circuit, we go to Analyze and Matching Circuit Generation. Let's add a band. .145 megahertz is our band, but you can also select a wireless system depending on what you're using. And I'll use a 10 megahertz span. Okay, and we'll check the topology. Two components is fine for us. You can have as many as 10. And for components, I'll be using the Coilcraft and Murata capacitors and inductors. I'll click OK. And there we go. It's generated a matching circuit. And you can see this uses a series inductor of 82 nanohenries and a parallel capacitor of 3.7 picofarads. So now that we have that, let's go ahead and see how these components perform in the real world. So before we go ahead and measure the matching circuit altogether, let's first measure the matching circuit with only the shunt capacitor or parallel capacitor included in the matching circuit. And for my test board, I've actually included a trace where we can do this. And instead of using a series inductor, I'm actually using a 0 ohm series resistor. And you can see I just have the parallel capacitor used in this case. And if you remember your matching circuit basics, a parallel capacitor, it moves the admittance in the clockwise direction along the constant conductance circles. So in this case, we've placed our matching circuit component, our impedance, roughly on the R equals 1 line, the constant resistance. So now all we need to do is we need to cancel out the negative reactance by adding a series inductor. And the series inductor will apply a positive reactance to get us to that middle center match point. Continuing on, now I have the series inductor added to the matching network, and you can see our match point or our impedance has moved closer to the center of the Smith chart. It's not perfectly at the center, and so to improve this, I'd probably repeat this process again to get the components exactly where I need them. But it's pretty close, and we can look at the difference between the unmatched case and the matched case by looking at the log magnitude. So now I'm comparing the difference between the unmatched case, which is in purple, with the fully matched case, and you can see that there's a significant improvement in how much power is being reflected. And you can see we didn't match perfectly, but we're getting a return loss that's below 40 dB at its minimum. So this is resulting in less than 1% of the power being reflected, whereas compared to this other case, you know, we're only getting minus 5 dB, you know, whereas maybe like 30 or 40% of the power is being reflected. So this yellow trace, the fully matched case, we're going to have much more power transmitted by our antenna and radiated out into the environment. So now let's look at the entire wireless system. And I have one antenna connected to port 1 and another antenna connected to port 2. And I'm measuring the path loss between the antennas, or the S21. And the purple trace here, this is the unmatched case, and the yellow trace is the fully matched case. And you can see I'm getting roughly 6.5 dB of improvement in the matched case, which if you calculate it out, equates to about 4.5 times more power being transmitted and received. Now this amount of power can significantly improve the performance of your wireless system and ultimately be the difference maker when it comes to successfully transmitting and receiving a signal. So this is why it's important to always use a matching network to properly match the impedance of an antenna with a transceiver. So just to summarize what I did in this video, I designed a matching circuit to match the impedance of an antenna with a transceiver module. And I hope you can see with the power of the TTR500 VNA, we can properly measure how much power is being transmitted. And the matching circuit is really important for getting optimal power transfer from your transceiver. For more information and videos like this, you can visit us at tech.com/TTR500.